regressor, or say independent variables, just like size of the house and age of child. And if we look at this figure in simple linear regression, we can see a straight line because this is linear equation. Why we call linear? Because beta 1, beta 0 are only a scalar. But x here can be x or x squared, no problem. So linear means the parameter is linear type. If x divided by beta 1, it's not linear for beta 1, right? So x times or x multiplied with beta 1, this is linear for the parameter. So for simple linear regression, we can show dependent variable and independent variable in a straight line in this figure. And beta 0 is the intercept, and beta 1 determines the line's position or the angle of this line. It's a coefficient. So we can see it's a deterministic relationship between two scientific variables. But why in real world, if the same child with same age, but they have different weight, and the same age or same size of the house have different price. So, which means in the relationship between x and y, there are plus some not deterministic factors, right? So, this is the concept of linear regression analysis, and we will use a statistical model to model this relationship. So, the actual y is the opposite of the value equals beta 0 plus beta 1 times x, also plus a random term. So here, this random term epsilon is a random variable that is assumed to be distributed with mean 0 and variance sigma square. And variance sigma square is the same for odd value of x. So this is very important. We will show later in the figure. And this is called homogeneous variance assumption for linear regression model. Say single linear regression SLR model. If we look at this figure, based on previous beta 0 plus beta 1x, this is straight line, we also plot the real opposite of the value. Because this is straight line, you will never know. You will never know. Nobody will tell you this is straight line. What's the beta 0 and beta 1. What we know is the opposite of the value for this point. This point can be stay here, can be stay here. For this x value, the point can be stay here, also can be stay here. But if we have many x value for the same x value, odd random term epsilon will follow some distribution which has the same variance, no matter which x value here is, right? So this is called a homogeneous random variable. So this is a very important assumption. If we look at this figure, x1 to x6, and this figure shows like a 3D figure in the two-dimensional space. So this is x and this is y. This is the deterministic relationship between x and mu y given x. So this line can be seen as the average value of a given x for the dependent variable, right? And this shape model the random term, the distribution of the random term epsilon. So that's why you can see you observe the value maybe here or maybe here, different value. But for the different x, their distribution of this random variable are the same. So the epsilon has the same distribution for different x value. So in a regression model, x or the independent variable, this is deterministic. This is not a random variable. Just like a house age and child age. This is deterministic, not a random variable. And what we observed, the value, like a house price, the weight of a child, this is random because this observed value has included a random term upon this deterministic relationship. And why we want to do analysis with the with the regression model? Because we want to know the parameter. And why we want to know the parameter? Because usually an analyst based on previous research results or from literature review, anyway from some known information and no theory, then build such a model, but never know the real beta 0 and beta 1. So we have to estimate these two parameters, but we never know. See, only what we know is the observed value for the y and the deterministic value of x, right? So from this value, we can estimate this regression line. We can estimate and using beta 0 for the estimation of b1 as estimation of the beta 0 and b0 estimation of for the beta 0 and b1 estimation of the beta 1, right? And this equation can be written as the y hat equals beta b0 plus b1 times x. So y hat is the predicted or fitted value from the estimated parameter. So beta 0 and beta 1 is estimated parameter. This is real value, right? And we show in this figure 1 is the theoretical value, but we never know this value for beta 0 and beta 1. And the other line, very close, but not exactly the same. This line is y hat equals b0 plus b1x. So this is estimated or say fitted line from the given observation of these scatter plots. And we look at these two equations. So yi is the observed value. For the fitted line, b0 plus b1 xi, we have to add ei. So this is the regression fitted line's error term. And for the theoretical regression line, yi equals beta 0 plus beta 1 times xi plus epsilon I. So epsilon I is the difference between the observed value and the deterministic relationship theoretically, right? But we never know these two parameters. So in this figure, you can see epsilon is observed value minus mu yx equals beta 0 plus beta 1 times x. And error term ei is the difference between observed value and the fitted value from estimation, right? So beta 0, b1, b0 and b1 here are the parameter estimated. So we can talk about the method of estimation. And the method of estimation widely used in regression model is the least square. So we should find b0 and b1, which are estimates of the beta 0 and beta 1, so that the sum of the squares of the residue is a minimum. So the estimation process is optimization problem. So we have to make a minimum of this error term in between the fitted line and the opposite of the value. And the residual sum of squares is often called the sum of squares of the errors about the regression line and is denoted by SSE. If you look at this figure again, this error term, EI, take sum, then put together this summation of these error terms square called SSE. So if we make this sum of the squares minimum, then we can say this line will be best fit with the theoretical line. So mathematically, if we want to get the SSE, we can just write this form. The difference between y is opposite of the value and the fitted value. Then take a square, then sigma for all the observations. Then SSE make differentiation of SSE with respect to B0 and B1. Because we want to estimate these two parameters. So we make differentiation. Then this is the result of the differentiation. And then we set these two partial derivatives equal to 0 and make some manipulation. Then we can get sigma yi equals this form and sigma xi yi equals this form. Then from these two, we can get the parameter B1 and B0. Actually, B1 is a division between the cross products between x and y and divided by the second moments of x with the mean of x. And beta 0 is a very simple form. So next we show an example using linear regression module. So this is a table of some data. The y value here and x value here. So y is the oxygen demand reduction and x is the solids reduction. So we estimate the regression line for pollution data in this table. So the solution is quite easy. We just fill all the data and get several results for xi sigma, yi sigma, and xi yi and xi square. I'll take sigma. Then we just fill this number in B1 and B0's formula. So we can get these two parameters. So which means y hat or the fitted line. This is the result for the fitted line. I'll say y hat equals beta B0 plus B1x here. And from this fitted line, we can also get 1 point estimation or prediction. Say, for example, 31% reduction level. We can get 31 reduction in the chemical oxygen. This is y hat when the x, or say the reduction in the solid is 30%. So next videos we will go into more details and assumptions and more advanced topics around linear regression module. Thanks for watching. So, welcome to our channel for probability and statistics. In this video, we will talk about the mean and variance of the estimators in linear regression. So we know linear regression is just a linear model used to find some inherent linear relationship among variables. So this is a simple linear regression model because there's only one x. Here x is the regressor or independent variable. And this is multiple linear regression because there are two independent variables, x1 and x2 here. So for the simple linear regression, we can use a straight line in the two-dimensional space to depict the relationship between x and y. So this is the beta 0 parameter for the intercept, and beta 1 is the slope of this line. And the estimation of the linear regression model is based on the idea that we will minimize the sum of the squares of this E1, which is the error between the observations xi, yi, and this fitted line. So y hat is the beta is b0 plus b1x. So b0 is just the estimation of the beta 0. Because beta 0 plus beta 1x is the real line, but we never know this parameter. We only can estimate using b0 and b1 here. So this line is called fitted line or linear regression line. So the estimation of the linear regression is based on the least squares, which will minimize the sum of squares of this error. So the parameter or the point estimate of b0 and b1 is b0 is the y bar, the average of all y value minus average of x value times b1, and b1 is the sigma of the cross product of xi and yi with respect to their corresponding mean value, then divided by the sum of squares of the xi with respect to the corresponding x bar's value. And we know it's very important that the values of b0 and b1 is random value, because this is just based on a given sample of n observations. So they are only estimates of the two parameters beta 0 and beta 1. So if we repeat the experiment again, we may not get the same value of b0 and b1. So which means b0 and b1 are the coefficients and estimates of the coefficients, or say the estimators, they are random value. They both are random value. Because if we look at the formula again, can see the b1, b0 based on the value of x and y, right? But here x a deterministic value. X are not a random value. Only y a random value. Yi, y bar, both are random value from sample to sample. So the y value, sigma y value are random value. Y value. So y value has a variance. So variance of y given xi equals sigma square. So this sigma square actually is the error term's variance. If we look back again, yi equals this fixed term plus an error term. And this error term is the counterpart of theoretically error term epsilon. So this EI has, we assume it has independent, identically distributed random variable, and its variance is fixed for different values of x. So this error term has a variance sigma square. That's why the y value also has the variance of sigma square, right? So after little complicated mathematical manipulation, we can get the mean of the parameter beta 1 is the actual real value of beta 1, and the mean of and the variance of the b1, this estimator also estimate, and the variance of the estimator b1 is this term, is the variance of the linear regression module, or the variance of the error term divided by the sum of the squares of xi with respect to x mean value. And mean value of the estimate b0 equals the real value of the beta 0. And the variance of the b0 equals error terms variance times sigma square of xi divided by n times the sigma squares of xi with respect to the x mean value. So it's very interesting. If the sum of squares xi with respect to x bar will be bigger, then the variance of bi will be smaller, right? For the same variance of error term. So this means, if we look back to the linear regression line, what this means? Because if we have the observations for the x and the y, if with x is a very small region, for example, starting value x here, ending value x there, so we only know x, y value between this range. So the variance of this slope b1 will be larger. But if we get x value very large, for example, starting value x here, ending value x there, so we get the range of xy in this whole range almost, then we get the very small variance of b1. So this is just like physics. If we get the very small range of x, this straight line like it's not very stable, right? It might shake from here, from there, not stable if we do many times of estimation. But if we every time get x range very large, then this straight line will be stable and get a small variance for this slope, right? Because we are very interested in this slope more than this intercept, and this slope determines the relationship between x and y. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about the partition of total variability and estimation of sigma square in linear regression. So this figure shows the linear regression, or simple linear regression between y and x. And this line is the true, a real linear relationship between x and y. But we never know this epsilon between observations and this real line. So this is the estimation of relationship between y hat and x. So y hat is the mean value for given x. So this line is the linear regression line. Y hat equals b0 plus b1 times x. So b0, b1 are the coefficients of linear regression. And the real observations, the difference between the observations and the point on this line, called E1, is the error term. So the coefficients of linear regression, B1 equals this formula, and B0 intercept is this formula. So next, we go a step further. There are three notations. SXX is the sum of squares between x and x bar, and SYY is sum of squares between y and mean of y. And SXY is cross product, sum of the cross product of x from x bar and y from y bar. So if we look back, so x bar is odd x values average between, from this regression line, odd x values. And the y bar, of course, is also for odd observations average. So these three notations. Then we look back again. So B0, x bar, y bar minus B1 times x bar. And B1 is this formula. If we check this formula, actually is SXX in denominator and SXY in the numerator. So B1 is XY divided by SXX. Next, we'll check the error sum of squares, ESS or SSE. SSE is the sigma of the squares. So inside the squares is the y value minus the regression or the mean value of the regression for given x. If we check the figure again, so SSE actually is the sum of squares of this EI, and this EI is the difference between real observations and the regression value of given x. So the difference between real observations and the point on this regression line, this difference is EI, and the sum of squares of this EI we call SSE. So SSE is the sum of the squares. Squares is the yi minus b0 minus b1 xi. So take square, and we go details for the mathematical manipulation. We can get the result of SSE is SYY minus B1 SXY. So these two notation we have seen here, right? And next we will talk about the estimate of sigma square. So what is sigma square? If we look back to this figure again, so this is the real unobserved. We never know this real line, but actually there exists and such line, right? Such line depicts the relationship between x and y. And here is mu x given x, y, and beta 0 plus beta 1x. So we write this coefficient here because we never know. Actually, we use a linear regression to estimate this. But for this real one, between observations and this real line, this is epsilon. And this epsilon confirms the hypothesis that this error, no matter which x value, this error follows an identical and independently distributed random variable. And this random variable in linear regression has normally distributed. And for the normal distribution, this random item has a variance called sigma square, or the variance of this normal distribution. And if we plus this one, this epsilon, then here will be the real y. So epsilon follows normal distribution with variance sigma square, which means the real value y also have variance sigma square, because beta 0 plus beta 1 times x, actually this is the deterministic term, then plus a random term of epsilon. So y value will follow this normal distribution. And in a simple linear regression, or say only one x independent variable, so the estimate of sigma square has this form. So this called S square is an unbiased estimate of sigma square. And the calculation of S square is SSE divided by n minus 2. SSE is the sum of squares of y minus y hat. So y hat is b0 plus b1 times x, right? So this is SSE, and SSE divided by n minus 2 will equal S2. So in simple linear regression, S2 equals SSE divided by N2. And SSE is also equals SYY minus B1 times SXY. And B1 is the linear regression coefficient estimation. So here y divided by n minus 2, not divided by n, because 2 means we lost 2 degrees of freedom in estimation of this linear regression, because there are 2 parameters. Because when we calculate SSE, we use 2 parameters. One is B1, another is B0. Because when we calculate B1, we use B0 also. So there are 2 parameters lost. That's why we divided by n minus 2 here. But S square is an unbiased estimate of sigma square. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will show how to calculate the confidence interval for regression coefficients in a linear regression model. So we know linear regression is just a fitted line to model the relationship between x and y in a simple linear regression model. And this line is the true line, but we never know these two parameters. So what we can do is to estimate the beta b0 and b1 from observed x and y variables. And this is the error term in model, which is the difference between the real observations and the fitted line. And this is the epsilon, is the real random items for a given x value and y value. And this epsilon has assumption that normally distributed with zero mean and variance sigma square. So for the different value x, this epsilon is assumed to have the same distribution. So the parameters estimate from the model is b0 for the intercept and b1 for the slope. And here all the estimation comes from the sample data x and y. Here y bar, x bar represent the mean value for x and y. And there are several notations very important: sxx, syy, and sxy. They're just the second moments of x from its mean and y from its mean, and across moments x from its mean multiplied with y from its mean. So from this notation, we can also write b1, estimation of parameter slope, actually the sxy divided by the sxx. And the sum of squared error, which is the sum of the square of error terms between observations and the fitted line, is syy minus b1 sxy. And another important item is s square, which is the SSE divided by n minus 2. So this term is an unbiased estimate of real epsilon of variance sigma square. So next we can talk about the confidence interval for the regression coefficients. Because we know the beta 1 follows a normal distribution, because estimation of the beta 1 comes from x and y. All x are deterministic variables and all y are random variables, because y observations is the fitted line plus error term, right? Because error term follows normally distribution. So that's why b1 also is random. So we can say for the different x and y, if we do again the experiment, we can get a different value of beta 1, right? So beta follows a normal distribution, and from the other videos or previous knowledge, can get n minus 2 times s squared divided by sigma squared. This item follows a chi-squared distribution with n minus 2 degrees of freedom. So this term actually equals this term is a division between a standard normal distribution random variable and chi-squared random variable divided by its degrees of freedom, then take a square root. So this division follows a t distribution with n minus 1 degrees of freedom. So we can get a 100% 1 minus alpha confidence interval for beta 1 or the parameter estimation. Then this item confidence interval, the lower bound and upper bound. So this item can also get from the sample, and this is a critical value for the t-half alpha. And this is the point estimate of beta 1. So we show an example. Find 95% confidence interval for the beta 1 in the regression line, beta 0 plus beta 1x based on the population data in this table. So we just calculate s squared from sxx, sxy, and syy. Then we can also get the s value and t 0.025 for 31 degrees of freedom from t distribution. Then 95% confidence interval for the beta 1 is just filling all the values in the formula from previous page. So we can get beta 1's confidence interval is about between 0.8 and 1. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about hypothesis testing on the slope coefficient in linear regression. So we know in linear regression or in simple linear regression, it's just a model to depict the relationship between y and x, where x is the independent variable and y is the observations or dependent variable. So this line is also called the fitted line or the linear regression line, with the y hat equals b0 plus b1 times x. And this line is used to as closely as possible to model the real line. This is the real line, but we never know. So in regression, we using the model to estimate the parameter based on the sum of squared errors of this term to be minimum. Then we can get these two parameters. And this error is called error term. EI is the difference between observations and the fitted point on this line. And this one is epsilon, is the error term in the real linear relationship. So this line is the real line given x value and the mean of the y value given x value. Because each observation is also randomly observed, randomly modeled, so based on this real line also we'll add an epsilon or random term in regression modeling. And these two parameter estimated, also called the point estimate for intercept b0 and slope b1, come from the observed data x and y, where x are deterministic variable and y is a random variable. And here we use some notations. For sxx actually is the second moment of x with respect to its mean value, and syy is corresponding for the y, and sxy is the cross product of x against x bar, x mean value, and y against y mean value. So we have this notation, we can get the point estimate b1 actually is sxy divided by sxx. Also, one important term in linear regression is called SSE, which actually is the sum of squared errors. So if you look back, the sum of squared errors of this term. So this SSE actually is syy minus b1, the estimated slope, times sxy. And S square also is the SSE divided by n minus 2, which is the degrees of freedom. So this one, S square, is an estimate of the epsilon's variance, sigma square. And this term equals SYY minus B1 SXY divided by n minus 2. Here we use minus 2 because two parameters B0, B1 estimated, so the loss of 2 degrees of freedom in the estimation of this regression line. So next we can do hypothesis testing on the slope. So the slope of B1 parameter is the most important, which we will focus on in the linear regression. And B1 comes from X and Y, and the Y value follows a normal distribution. So B1 also follows a normal distribution. And the one term n minus 2 S squared divided by sigma square, so here is the square, follows a chi-squared variable with n minus 2 degrees of freedom. So this term T, which is a division of two parts. So you can see the enumerate actually is a standardized normal distributed random variable, because B1 minus its mean and divided by its standard error. So this item follows a standard normal distribution, and S divided by sigma follows the square root of a chi-squared distribution random variable divided by its degrees of freedom. So based on the definition of T distribution, this item is a division of a standard normal distributed random variable by the square root of a chi-squared random variable divided by its degrees of freedom. So this term follows T distribution with n minus 2 degrees of freedom. So this T actually is B1. This is the estimated point for the slope minus its mean value, the real value of a slope, divided by the S divided by square root of S-axis. So this term follows T distribution with n minus 2 degrees of freedom. Then we can test the null hypothesis that beta 1 equals beta 1 0 against a suitable alternative hypothesis. Can use the T distribution to get to the critical region. So next we look at an example. So with the following table data for X and Y, we can get the point estimate of B1 in a linear regression is 0.90. So the question is test the hypothesis that B1 equals 1.0 against the alternative hypothesis that B1 less than 1.0. So this problem actually is a one-sided t-test. So we form the hypothesis H0 is B1 equals 1.0 and H1 or alternative hypothesis is B1 less than 1.0. So we calculate the t value, then fill in the value of estimate the point B1, and 1.0 is the value we against in the test, and divided by S and divided by the square root of sigma. Then this value is minus 1.92. And this value follows 31 degrees of freedom of a T distribution. And in one-sided test, we can get the p-value which equals the left side of this value and a T distribution density curve. So this area is about 0.03. So this p-value is quite small, or say less than 0.05. So we can say the test is significant in this hypothesis testing on the slope. Or we can say we have relatively strong evidence suggesting that the beta value less than 1.0. Or say the linear regression's slope less than 1.0 from given observed data in our problem. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about statistical inference on intercept in a linear regression model. So we know linear regression is a model just used to illustrate the relationship between independent variable x and dependent variable y using an equation with the parameter beta in a linear type. So this is the real relationship between x and y. So we just use the notation mu y given x equals beta 0 plus beta 1 times x. So here mu means the given value, the mean value of y given x. So for each x, the y variable here may be random. So that's why we add the random term. So in the real relationship, the random term is epsilon, follows standard normal distribution with variance sigma square. And this line y hat equals beta 0 plus b1 times x. This is the linear regression line because we never know the real line. See, we only can estimate the real line using this linear regression equation. And this term ei in formula represents the error term between observed value and the fitted point on this line. So using the least squares method, we can get the point estimate of the b0, which is the intercept of the linear regression line, and the slope b1. So just coming from old x and y value, here y bar, x bar, the mean value in a sample. And there are several useful notations in the regression model. So we can recall SXX is the sum of square of x with respect to its mean value. And similarly for the SYY and SXY is the sum of the cross product of x and y with respect to their corresponding mean value in the sample. So from this notation, actually, the point estimate B1 equals SXY divided by SXX. And another notation is SSE, which means the sum of squared error. If we look at previous figure, so SSE actually is the sum of EI square. EI is the difference between observed value and the fitted line given x on this point. So SSE actually is SYY minus B1 times SXY. And S square, which is SSE divided by n minus 2. So this term is an unbiased estimate of epsilon, the variance sigma square. So next we can say the statistical influence on intercept. So because beta 0, because you estimate the beta 0 is the real, is the is estimated intercept, and this intercept, if we resample many times, we can show this estimated beta 0 also follows normal distribution. Then the t statistic, which is beta 0 minus an hypothesis real value divided by this term. So this term is a chi-squared random variable. Take square root and divided by its degrees of freedom. Although it seems a little complicated, but this term is square root of the chi-square distributed random variable divided by its corresponding degrees of freedom. So a standard normal distribution divided by a square root of chi-square distribution. So this term follows t distribution with n minus 2 degrees of freedom. So we can construct confidence interval from this term. So next we show the confidence interval from beta 0 for the intercept. So this intercept is estimated value if we resample many times. So this intercept's confidence interval is lower bound here, and this is upper bound. The point estimates minus and plus a term. The term is the t critical value, t half alpha, times this term. So there's an example. Find 95% confidence interval for beta 0 in the regression line. So this estimates the mu y given x, beta 0 plus beta 1. We focus on beta 0 here, and from this table. So first, from the notation and the formula, we can get sxx and s is the square root of s square, and sigma xi square, and b0, the point estimate for the intercept. Then we can, from t distribution table, find the t critical value for 0.025 because we want to get 95% confidence interval. So alpha is 0.05, so t half alpha is t 0.025. And for 31 degrees of freedom, this critical value is 2.045. Then we fill all the items in the confidence intervals formula. We can get the estimate for the intercept confidence interval is between about 0.21 and 7.44. So you can see this confidence interval does not cover 0. So which means estimate of the intercept is not 0, which means that beta 0 is significant. So if this confidence interval covers 0, so which means it is possible that the beta 0 equals 0. So in this case, this linear regression is called regression through the origin. But actually in this example, it does not through the origin because there is an intercept of this regression line. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will introduce coefficient of determination in linear regression. So the coefficient of determination, also called R-square, is a value that represents or measures the proportion of a variability of the variable explained by the fitted model. So mathematically, R-square is 1 minus SSE divided by SST. So where SSE called sum of error squares or error sum of squares is the sigma square of the y variable minus the y hat. Y hat is the fitted value. So this is the error term. Then take a square. Then sigma for all the observations. And SST is odd y value minus the y mean value, mean of y, then take a square, then take a sigma for all the observations. So if we look at this figure, it will be more clear. So this is the y bar. For the linear regression, all the y values has a mean value, y bar, right? And for this individual y, yi is an observation here. Then y hat is this point, because this is the linear regression of fitted line. So on this point, for a given x, then this y value is y hat is the fitted y value. So observations minus this y hat is the error term. And observations minus this y bar is the deviation from the mean. So you can see from the formula for determination of coefficient of determination, actually this range between yi and y mean value, then take square, then sum for all y observations is SST. And this part between the observations and the fitted line, then take a square, then sum for all the observations, this is SSE. So the coefficient of determination measures this part, right? If this part is very close to 1, so which means the error term will be very small. So which means all the observations, all the variance of the y, because y observation minus the mean value take a square is the variance, right? So all the y variance will be explained by this fitted line. So this is a very perfect model. But on the other side, if error term is very big, only very small part of the variation for the y variables explained by the model. So it's a very bad model. So this figure shows two kinds of model. So this is the y bar, and the point is the y observations, and this is fitted line. So in this linear regression, R square will be very big, very large, almost close to 1. Because you can see the error term very small, the point is very close to its fitted line, which makes the error term very small. But on the other side, this figure shows a very low R square for the linear regression, because the point is very far from the fitted line, right? So coefficient of determination measures the variance of y variable determined by or explained by the fitted line in linear regression. But one thing is, this coefficient of determination will never decrease if you add more explanatory variable. So which means if you make the model very complex, you will increase this coefficient of determination. And actually this is what we want, right? Because we can add many unrelated model, unrelated explanatory variable into the model. So this is called overfitting. So very important is that we may not arbitrarily focus on the coefficient of determination. Although this coefficient measures the variation explained by the model, measures the explanation power of the model, but we cannot arbitrarily focus on only this coefficient by including more and more independent variables. So this is a balance between the model compactness, and this compactness based on the theory and based on the discipline in your subject, and based on the previous research by other people. So then we can add the most interesting variables into the module, then can measure this coefficient of determination. Then go this way, can compare between two models or among many different models. So this is only one part of the model measurement that we can use, not the only thing saying the model is better or worse, right? Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about prediction with linear regression. So when we have estimated a linear regression model, so one of the purpose application is to estimate a predicted response value at given values of explanatory variable. So there are two notions about prediction. One is to predict the mean response given specific values of independent variables. And this is actually the value which lies on the regression line. And we want to estimate the confidence interval of this value. And the second idea is predicting a single response value given specific values of independent variables. So this is a more random, the values or confidence interval, or we say prediction interval, than the first one. So if we look at the linear regression results, so mu y given x0. So this is the given values of x, then the mean values of y. And this is actually the value of the regression line. So we just fill in the estimated beta 0 plus beta 1 times x0 will give this mu y given x0. And the variance of this one is this term. So sigma square is the error terms epsilon's variance, or the linear regression, or the variance of the observed value. And this is sample size, and x0 is the given value of x. We want to predict y upon this value, and x bar is the sample mean value of x, and sxx is the sum of the squares of x against its mean value. So 100 times 1 minus alpha % confidence interval for the mean response mu y given x0 is y hat. So y hat actually is this one. Is the value just fill in x with linear regression line. So y hat minus t half alpha times s, and s is the sample, the standard deviation of the variance of this random term, and square root of 1 minus n plus this term. And the up bound is y hat plus this term. And for the prediction for single future response, actually the point estimate is the same, is a y hat, but we have to add more randomness. So here will be 1 here in addition to this term in variance part. So this confidence interval, as we say prediction interval, is more wide than the mean value of y given x. So we take a look at an example. using the data in the table, construct a 95% prediction interval for y0 when x0 is 20%. So after we have estimated this linear regression, we got odd items in sample size 33, x0 20, x mean 33, and the y0 hat. Just fill in the beta value, we get 21.9. Sx is about 4,100 and S 3.2. If you want to note how to calculate Sx, X, and S, you can just check the playlist's other videos. We have details about these notions in linear regression. Just check the recent videos in this playlist. And T half alpha is 2.045 for 31 degrees of freedom. So a 95% prediction interval for y0 is between these two bounds. So we get the result about 15 to 28. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about using analysis of variance approach or ANOVA approach to analyze the linear regression model. So say we have a simple linear regression y with independent variable x. So one aspect of analyzing or evaluating the model's explanatory power is to check the variance explained by the model and not explained by the model. So this approach is called analysis of variance approach. So we will subdivide the total variance of the dependent variable into parts. So first we say from the linear regression estimation we can get this equation. SYY equals B1 times SXY plus SSE. Here B1 is the slope parameter coefficient, and if we look at notations in linear regression, SXX is the sum of x against its mean value take square, and SXY is the sum of the cross product of x and y against their mean and take square, and then take sum. Right? And SSE actually is the error term between the observations of y and the fitted value of y. So this is the fitted value of the y. So this error term takes square and takes sum. We call SSE. So SSE equals SYY minus B1 SXY. So if we go further, we will write in this form. So SST is the total variance of y against its mean, take square and take sum. And SSR, called regression sum of squares, actually is the fitted line. It's the fitted line minus the y mean values take square, then take sum. And the last term called SSE is the regression sum of the sum of the squared errors. So this term is the sum of the squares of the error term, which is between the opposite of the value and fitted value. So this equation called partition of total variance in the regression. So SST equals SSR plus SSE. So we can look at this table. This is ANOVA table, analysis of variance for the linear regression. So SST equals SSR plus SSE. And then each term have their corresponding degrees of freedom. And we can form and null hypothesis that beta 1 is 0. So beta 1 is 0 means this module does not exist. Actually, no explanatory power for the x variable for the y dependent variable. So this is a null hypothesis. And against an alternative hypothesis, beta 1 not equal to 0. So we will use this ANOVA table, then form an F statistic, which is a division of SSR by the SSE and their corresponding degrees of freedom in the denominator. So this actually is SSR divided by S squared, because SSE divided by n minus 2 divided by its degrees of freedom called S squared. S squared is an unbiased estimate for the module's variance, for the y variable's variance. So we have this f value. So just if this computed f statistic exceeds the critical value in f distributions density curve with 1 and n minus 2 degrees of freedom, then we will conclude that there is a significant amount of variation in the response accounted for by the postulated module. So this module is a regression line. And on the other side, if f statistic is in the fail to reject, then we will conclude that the module or the data did not reflect sufficient evidence to support the module postulated. So this F-test is to say we test this module by total, because this module has only one independent variable. So this is the same as we test beta 1 is 0 or not 0. So if this module is multiple linear regression with more than one independent variable, and F-test approach or analysis-of-variance approach can also apply. So this also says if the significance of the F-test, which means in the sum in the combination of these couple of independent variables, has explanatory power for the model to estimate the dependent variable. So this is command summon for F-test. But for the simple linear regression with single independent variable, F-test equal to a t-test for the beta 1 0 against the beta 1 not 0. Because in a single variable, the t-test statistic take a square exactly equals to the F-test. So this is just another alternative approach to the t-test for the beta 1 not equal to 0. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we'll talk about test for linearity of regression module. The test for linearity also means test for model appropriateness. Because in linear regression, in simple linear regression, for example, we assume that there is no second power of the independent variables in the module. So if say we omit some very important information which come from the second or third power of one of the independent variables, so we say the module is not appropriate and the module is not linear in terms of the variables. So how to test for the appropriateness of the module? So one way is using repeated observations. So this means in a given x variable, and given independent variables value, we will test and get several observations of y. So say for x1, x2 until xn, and we get ni for each of these xi's values, observe the value for the y. So say for example x equals x4, a given value of independent variable, and we get 3 measurements of y. So we denote ti dot equals the sigma of odd y values for this given x value. Then we divide it by this ni, we get the mean of yi dot. So this value is the mean value for given xi's y value. So we need this value because for the given xi, so x is fixed, but we get a different y value. So this difference from the y value is a pure random variable. So this is a pure random variable and is not connected with the module. It's not connected with the modeling because we need a pure randomness in testing for linearity. So in the linear regression, we get the fitted module, fitted line, and we have the real observations. The difference between these two is called error term. And actually this error term is a combination of pure experimental error and another term which is called lack of fit contribution. So lack of fit error, if it's very big, so the model is not appropriate. So we hope the lack of fit error is as small as possible. I'll say the most of errors come from pure experimental error. And this pure experimental error, we have used repeated observations to test. So next, we will denote several important items. So this SI is actually the sum of error terms for given xi's y variable, right? So for one of xi independent variables value, we get odd y value, then minus this y bar for the given xi. Then take a square and divide it by ni minus 1. So this is called SI square, and we sum all the SI squares, then putting this old SI and divided by n minus k. So we get this SI is the real pure random errors SI. So if we look back one page, so in the real, if the model is correct, then old SI S square comes from the pure random error. And this term will actually equals SSE divided by n minus 2. So SSE comes from the sum of error squares using the difference between observations and fitted value. So SSE divided by n minus 2 in a correct model is the same as S square. S square is a pure random error item. So these two will be equal. And SSE and this item comes from SSE divided by n minus 2 will be an unbiased estimate of sigma square, which is the model's error term. But if the model is not correct, if we omit some second power terms or third power terms, then this 2 is not correct. This is not correct. So we use this table will be more clear for the idea. This is SST, the total sum of square. If we have learned the basics of linear regression, you know this term actually is the sum of difference between y observations and y mean values, or sum of these differences square. So this is SST, and it has degrees of freedom n-1. So this table is like an ANOVA table, analysis of variance. And SST has two parts. One is SSR, another is SSE. SSR is sum of variation due to the model, due to regression. So this is the term of the value on the fitted line and between this item and the mean value of y. So this term has 1 degree of freedom. Another is SSE. SSE, we have said that is the difference between the observations and the fitted value. So SSE and SSR combined is SST. So now we will focus on these two lines. So if the model is not being done correctly, so SSE will have two parts. One is SSE, we call it pure. This is the same as we have shown in the previous page that we use repeated observations for given x value. So this is SSE pure comes from the repeated observations, pure randomness. And another part is SSE minus SSE pure. So this is the lack of fit item. So this is all their corresponding degrees of freedom, and this is the item divided by its corresponding degrees of freedom. So in a real model, in a real correct model, we can use these two is for the f value. If the model is correct, we just use this to test if the model is significant, or say the odd independent variables can explain the model, like something that. But now we focus on these two parts. So S square is SSE pure divided by its degrees of freedom. And SSE and the lack of fit is the difference of these two parts and divided by its degrees of freedom. So this part is the f value because these two parts both have chi-square distribution with degrees of freedom. And division of these two parts divided by their corresponding degrees of freedom will follow an f distribution. If this part is very small, under the assumption we will test this part. So the null hypothesis is the lack of fit is very small, is 0. So under this assumption, this term will follow f distribution with these 2 degrees of freedom. So if this f test is significant, then we will reject the null hypothesis and this term will not be 0, which means the model is not fit good, right? We have omitted some important items in the model. So this test is significant, which means the model is not appropriate. So next we will show an example. So this is data, all the x values and all the y values. So you can see for the given x value, we have repeated observations for the y. Then we will test if the model is fit correctly. So we just calculate all the items in this ANOVA table. So the result is this one. This is the F-test result. You can see the p-value is quite large and much larger than 0.05. So the test is not significant, and we will not reject the null hypothesis of lack of fit is 0. So which means the model is correct, right? Because the test is not significant, and this lack of fit is very small compared with the pure error term. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about data transformations in linear regression. So we know linear regression means the linear in parameter. So like this equation, both the parameter beta 0 and beta 1, a linear form. If say the beta 1 is in the power of xi power beta 1, so this parameter is not linear, and we cannot say this is a linear regression. And sometimes the data relation between y and x are not in parameter linear type. So we may perform a transformation based on real situation to get a linear regression. And some typical forms of the nonlinear relationship listed here. This is exponential relationship between y and x. And this is the power form. And this is a reciprocal relationship between y and x. And this is a hyperbolic. So after transformation, we can return a linear regression between the transformed variables. So after we have estimated these transformed variables in a linear regression, then we can transform back to the original type of the parameters or the coefficients we are interested in. So according to the left side of this nonlinear relationship, we can transform here y star is the longer y. And for the power relationship, we can transform both x and y with the log formation. And for the reciprocal, it is understandable that we can transform the independent variable with the reciprocal form. And for the hyperbolic, we can transform both x and y in inverse. So next we will show some graphs. So this for A, B, C, D, which representing the equation in previous page for the exponential power relation and reciprocal function and hyperbolic function. So we show an illustrative example to show how to return a linear regression when the relationship between x and y are not linear. So the pressure P of a gas corresponding to various volume is recorded and the data given in the table. And the ideal gas law in the physics has this form. So PV with the gamma in the power of V, the result is C. And gamma and C are constants. So the question is estimate the constants C and Y. Now this is a power relationship between P and V and not linear. So if we want to use linear regression to estimate the coefficients, we have to transform the variable. So here we transform both x and y in the longer form. So for this original equation, we can get this transformed equation. So this is a linear relationship because gamma is in the linear form. although the log of v and the log of p are not equal to the original p and v, they have transformed. But we can estimate this equation in a linear regression. So after we have transformed all the values for all the observations, then this equation can be estimated, and we get the coefficients, so intercept in the linear regression, and for the constant c, just get the power of this relationship, this log c. And the slope gamma in the linear regression can be estimated also. So c and gamma have been estimated after we have transformed the variables for x and y. So here x is the v and p is the y. So both constants are estimated. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about correlation, slope coefficient, and coefficient of determination in linear regression. So first we will talk about correlation between x and y. So here x is independent variable and y is dependent variable. And also in linear regression, we often assume that the independent variables x are physical or scientific variable, not at a random specification. But in reality, all the variables are random, because in the linear regression, we often assume that in a given x, there are random variable y. But actually, x itself can also be denoted as a random variable because x range different values in the sample, right? Because we get a sample and we do not know exactly beforehand what the value of x is. So x and y actually, they are both random. So, which means x and y has correlation coefficients if they are correlated. And if we look at the regression model, so y is beta 0 plus beta 1 times x plus epsilon. So this is epsilon is independent random variables with x. So epsilon itself has variation with a variance called sigma square. And if x is random, x also has variance sigma x squared. And because they both two are independent, so the variance of sigma y is the sum of sigma square plus beta 1 square times x variance. And the mean of y, given mean of y is the mean of x times the coefficient plus the intercept. So here beta 1 is the slope coefficient. Because x and y both random, so they have a joint distribution. So this is the joint probability density. It's a very complicated, but actually is the multiplication of these two random variables, then plus a parameter called rho. So here rho square is a division of sigma x square divided by the sigma y square times beta 1 square. So if we look specifically this equation, so the value rho is 0 if beta 1 is 0. So the rho is correlation coefficient between x and y. And the relationship between the correlation coefficient and the slope coefficient is this equation. So when beta 1 is 0, which will result when essentially is no linear regression, because the slope is 0. So y is not connected with x. And in this case, their correlation coefficient is also 0, right? And because sigma square y, here sigma square y is larger than the sigma square, So we must have row square less than 1 because this division is less than 1. So 1 minus this one, which means this part is less than 1. So the row square is less than 1. And row also between minus 1 and 1. So the correlation coefficient between two variables is scale-free. It should lie between minus 1 and 1. But the slope coefficient is not necessarily between minus 1 and 1. It is not scale-free. So the beta 1 can be any value, right? So this is different, and their relationship is with the multiplication of sigma x squared divided by sigma y squared. So this is the relationship between the correlation coefficient and the slope coefficient in the linear regression. And if we denote R as the correlation coefficient, we just change the alphabet. R is same as correlation coefficient. There will be another equation. Its value is the division between sxy divided by the square root of sxx and syy. What is this three parts? So syy is the sum of the square of y variable against its mean. So it is the sum of the square value. Inside the square value is each y minus the y mean value. So average of y, all the sample. Then take a square for all the observations. So this is syy. And the same for the sxx is the sum of all the observations x variable against its mean. Then take a square, then sum together for all the x variables. And sxy is sum of all the multiplication between x against its mean times y against its mean. So x minus x mean times y minus y mean. Then take sum for all the observations. So this division equals correlation coefficient. So this is our correlation coefficient, the same as previous page. We just changed the alphabet. And if we take a square root, this one is also has in the linear regression aspect, it's a division of SSR divided by SYY. If we take a square of this R, then the value is SSR divided by SYY. What is SRR? SRR is the module of y, odd y variation explained by the linear regression model. If we look at this is the linear regression line, and this is the y mean value. And this part is SST, the total y variation is also called SST. Then this is the SSR. This is SSR. And another part is SSE. So SSR is the variation of YY, is the variation of the module explain the total variance of YY. So this R square we can also call coefficient of determination, represents the proportion of the variation of SYY explained by the regression of Y on X names SSR. So R square in every linear regression module result will have this value. It is between 0 and 1. So say R square is 0.95. So which means the variation of Y variable SYY can be explained by the module 95%. In a simple linear regression model, which means it's only one independent variable, X, then the coefficient of determination R square, then take a square root, will equal to the correlation coefficient between x and y. So this only applies in simple linear regression. This two value is just the square relationship. So in conclusion, in the linear regression, correlation coefficient between x and y is actually the square root of coefficient of determination. And correlation coefficient between x and y is also equal to the coefficient equal to the square root of the coefficient, slope coefficient beta 1 times sigma x square divided by sigma y square, then take a square root, is also equal to the correlation coefficient. So this is the relationship between the correlation coefficient with the other two items in linear regression. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will introduce multiple linear regression model. So when we want to estimate a response, so response is a dependent variable from more than one independent variable, and if the parameter behaves as linear in the model, so this is called multiple linear regression. So we use this form, mu y given x1, x2 until xk. With this means the y is the mean value given x variable, and this is the module. This is the module. So the module is the fitted line is to estimate the mean value of y given range of independent variables with a series of parameters called beta 1, beta k. And this is the estimation of the module. Y hat is the mean value of the y given x variable. And b0, b1, b2 until bk are the coefficients estimated from the module, because we never know the real value of this beta, right? What we can do is to estimate the beta, and using the coefficients is the result of the estimation. And how to estimate the coefficients of multiple linear regression model? So we use the sum of error terms square. So EI is the difference between real y value observations or the response value and the fitted value B1 plus B1 plus B2 x2i plus until bkxi. This is the fitted value from the previous page, right? This is the y hat. So yi minus y hat, take a square for all y observations. So this is called SSE, sum of squared error. So we will minimize this sum of squared error. Then we can get a series of equations. This is called normal equations for multiple linear regression. You can see all the equations except the first one. So next, all the equations, the key equations is x variable or xi's variable, then plus its square, then its multiplication with all the other x variables. So this is same for all the x1 to xk. So totally, this is called normal equations, because from these equations we can use optimization techniques to get estimation of the parameter b0 to bk. So next we will show an example using multiple linear regression. The study was done on a diesel-powered light-duty pickup truck to see if humidity, air temperature, and barometric pressure influence emission of nitrous oxide in ppm. And emission measurements were taken at different times with varying experimental conditions. The data are given in the table. So this is Y, and this is X1, X2, and X3. So the question is to fit this multiple linear regression model to the given data, and then estimate the amount of nitrous oxide emitted for the conditions where humidity is 50%, temperature 76 Fahrenheit, and barometric pressure 29.30. So the solution is first we will establish this multiple linear regression, beta 0 plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i, and this is epsilon, the random term, and I from 1 to 20 because we have 20 observations. So then we can estimate the B0, B1, B2, B3 from this regression model, and all main software for the statistics can estimate this equation very easily. And we can get the value, then set in this value with the equation. So y hat here is the mean value of given xi. Y hat equals the right side is the coefficient and x as independent variable. So for these values of independent variable, we just fill in the value, can get about 0.9384 ppm for this y value. We have to note this result is to say for the given x1, x2, and x3, this particular value, the mean value of y. This is the mean value of y for the given xi. So this is what linear regression, what a multiple linear regression explains. Thanks for watching. So, welcome to our channel for probability and statistics. In this video, we will talk briefly about polynomial regression. So we know multiple linear regression means there are more than one independent variables in the equation to estimate or predict a response variable y. And the polynomial regression actually is a special case of more general multiple linear regression model. So in the polynomial regression, different dependent variables actually comes from a single independent variable x, and it exists as x first power, x second power until x rth power. Because the parameters are still in linear type, because this is linear type for the multiplication beta 1, beta 2 until beta r. So this is also linear regression, a special case of multiple linear regression. And we can also use the same estimation method for minimizing the residual sum square. Then we can get several normal equations to estimate the parameter beta. So this is the normal equations. After we differentiating SSE, sum of squared residues, then with respect to this parameter, then we can get these normal equations and estimate the parameter beta 1, beta 2, beta k. So next we look at an example. So given the data in a table, to fit a regression curve of the model mu y x equals beta 1, beta 0 plus beta 1x, plus beta 2x squared, and then estimate the mu y given 2. If we look back, because in multiple linear regression, there's two parts. The first part is the fixed part, with the parameter multiplied with variable. Also, the variable can be power type or other variable. And the second part is the random term, epsilon. Epsilon is assumed as same variance for different values of x. And the fitted model, this is the fitted model, no epsilon. So mu y given x is the meaning of the mean value of the y given x. So for the same fixed x variables, the y variable is random. So that's why we write here mu y given x. Because y is two parts. The linear part with the x and the parameter, and the random part. So y is a random variable even for the given x value. That's why the fitted model, the linear regression line, is the mean value of y given fixed value of x. So that's why here what we can do is only estimate the mean value of y given x variable. So it's quite easy. We just fill in all items in the normal equation. Here, 3 normal equations cause 3 parameters. Then can estimate beta 0, beta 1, and beta 2. Then the mean of y value given x is y hat. So y hat equals this equation, x and x power. Next, we can fill x value 2 here. So the mean value of y given x is 2 is 5.168. Thanks for watching. So, welcome to our channel for probability and statistics. In this video, we will talk about estimating linear regression model using matrices. So we know if in a multiple linear regression model, when the number of variables, or say the number of independent variables exceeding 2, so you have to use matrix knowledge to understand in detail of the regression estimation. Let's say if in a model there are k independent variables, x1 to xk, and n observations, y1 to yn. Then for each observation, we can write yi equals the production of parameter beta and each independent variable, then plus and the random term epsilon I. So if we want to express with such an equation for all observations, so we have to use matrix notation. So we can write y equals x beta plus epsilon. And here y is a column matrix with the shape n1, because there are n row and 1 column. And x is matrix with n and k plus 1. Because there are n observations for each row and k parameters plus 1. 1 is a scalar. Then beta is also a column matrix with the shape k row and 1 column. And the same for epsilon is n1 shape in matrix. So this matrix times beta will get a matrix with the shape n1. Then n1 matrix is compatible to the addition with the epsilon. Then the result will have the same shape as Y matrix. So if we know this matrix expression, then the estimation of linear regression model is to minimize this term called SSE, sum of squared error. And the sum of squared error actually is the matrix multiplication with the Y matrix minus XB, then do transpose, then multiply with Y minus XB. So the result is a scalar, is only one number, SSE. Then this number, this item is expression of the parameter beta because we do not know the beta value. Then using derivative and optimization technique, we do partial derivative of SSE with respect to B vector. And this item we will minimize. Then we will get the value of B. And the result of this optimization and minimization process will return this expression after mathematical manipulation. So X transpose times X then times B will equal X transpose times Y. And this comes to actually a series of equations, and these equations called normal equations. And each equation except the first one actually is the sum of the second power. Second power, which means either is independent variables square or product of each pair of independent variable. Then this series of normal equations can be written as AB equals G if we denote X transpose times X is A, and G is X transpose times Y. So XB equals G, this is normal equation. Then the estimation of this equation is possible if A matrix is not singular matrix. So what means singular matrix? Singular matrix is the determination of this matrix is 0. So if A's determination is not 0, so we can get the result of B is this expression. Is the product of A X transpose with X itself, then we take inversion. So this part is the inversion matrix, then times X transpose times Y. So the result of B is a column matrix. The shape is K row 1 column because we have K parameter. So next we will show example using matrix expression to estimate the linear regression. So the percent survival rate of sperm in a certain type of animal salmon after storage was measured at various combinations of concentrations of 3 materials used to increase chance of survival. And the data given in the table estimate the multiple linear regression model for the given data. This is the data table Y, X1, X2, X3. So the least square estimation equation is this equation. Is the product of X transpose times X then times B equals X transpose times Y. So we can write in the matrix form, this is the product of X times X transpose, and this is the B, and this is the X transpose times Y. After we have filled in all values. And for computer readout, we use computer to calculate we can get the inverse of this matrix. Is the 4 times 4 matrix. Then B equals this value, this expression. We just fill in all matrix, then we can get B's value. B0, B1, B2, B3. So the estimated multiple linear regression model is y hat equals B parameter times x variables, and here y hat means the mean value of given independent variables value. In this video, we will talk about multiple linear regression using analysis-of-variance or ANOVA approach. So we know multiple linear regression means there are more than 2 independent variables in linear regression to estimate or predict one response variable y. And there are several notations used in multiple linear regression, which is the same as in a simple linear regression for separating the error terms in the model. So this is the basic equation called SST equals SSR plus SSE. This is equal. And this part called SST, which is the sum of the squares of the difference between y value and the mean of y value. So this is the variance, odd variance of y. And this part, SSR, this part equals y hat. Y hat is the value on the regression line. So this is the fitted value of y. So sum of odd squares of the difference between fitted value and the mean value. So this is the model's power to capture the variance valuation of y value. And this part is error terms sum square called SSE, which is the sum of the squares of the difference between observed y value and the fitted y value. So this part is error term, which is the model cannot estimate. So if this part is very large compared to this part, so if SSE very large compared to SSR, then which means the model is very little power to capture the variance of y. And so we hope in ANOVA or analysis of variance approach, we hope this part as large as possible. So in this approach, there is H0, a null hypothesis says beta 1, beta 2, beta 3 until beta k all are 0. So which means the model is nothing, just a constant term. So if this is true, then SSR, SSE has degrees of freedom, and we divide SSR and SSE with their corresponding degrees of freedom. So this is called mean SSR and mean SSE. And under this assumption, these two parts follows chi-square distribution, SSR and SSE. So the division of two chi-square distributed random variable with their corresponding degrees of freedom follows an F distributed random variable. So analysis of variance approach using F test. So this part is the division of these two parts, and these two parts follows chi-square distribution. So which means the division is a F statistic follows F distribution. So after we have tested this F test, this is an up one-tailed test, which means one-tailed test. So if this test larger than the critical value, or which means the p-value is less than 0.05, then we will reject H0. So reject H0 implies that the regression equation differs from constant. So which means if the test is significant, we get the conclusion that not all beta coefficients are 0, which means at least one regressive variable is important to predict the response variable. Hello. In this video, we will talk about hypothesis testing of coefficients in a multiple linear regression model. So when we have estimated a multiple linear regression model, usually we want to check if the individual coefficient is significant or not. So this is called hypothesis testing of the coefficients. So we use matrix notation for multiple linear regression model. So these are matrix type. Y is n times 1 size of matrix. Actually, it's a column matrix. And X is a matrix with n observations and k variables. And beta is a row matrix with k variables. And this epsilon is the variance matrix. So this epsilon, we hypothesize that this is normally distributed with variance sigma square. And this matrix is very important to be used in coefficients estimation. So actually it's the inverse of the transpose of independent variables matrix. So this comes from the information for all the independent variables. So after the regression model has been estimated, we get the point value of the coefficient bj for all j from 0 to k. So this is k plus 1 coefficients. Then these coefficients are normally distributed with the mean called beta j, which is in regression model with the real value, and with a variance called Cjj times sigma square. So Cjj comes from this matrix. So each coefficient theoretically follows a normally distributed distribution with the beta j real value, and this is the variance. But we never know this one, and we never know the variance of the epsilon, sigma square. So what we can do is only use the test statistic called T, which is the point value beta j minus this is the value what we want to test, and divided by the projection of two parts. The first part is the square root of Cjj from this matrix, and second part is the S. S is sum of square error. This is called SSE, then divided by n minus k minus 1, then take a square root. So S is actually a point estimate or unbiased estimate of the square root of this variance. So because we never know the real value of sigma square, we use S here. So this statistic follows a T distribution with n minus k minus 1 degrees of freedom. So we can use this statistic to test the hypothesis of the beta value. So say if we want to test if this beta coefficient is equal to a specific value, and this is the null hypothesis. For example, this is 0. So if we want to test the beta j equals 0 or not, So we formulate alternative hypothesis is beta j not equal to this value, not equal to 0. Then, if we get the statistic from t from the last page, if this t is located at both ends of critical value in the t distribution density curve, in the shaded area for both sides, but here will be, if we test two sides, this is half alpha. So say if alpha is 0.05, so this area will be 0.025, and other side also. So if the t value is very large or very small, then we will reject null hypothesis and will in favor the H1 alternative hypothesis, which means we conclude beta j is not equal to this specific value. So next we look at example. The percent survival rate of sperm in a certain type of animal salmon after storage was measured at various combinations of concentration with the material used to increase chance of survival. And the data shown in the table in the next page. And the question is, we want to test beta 2 equals minus 2.5 at 0.05 level of significance against alternative hypothesis that beta 2 larger than this value. This is the data table y, x1, x2, x3. This is multiple linear regression with 3 independent variables. So from the question we formulate, this is a null hypothesis, beta 2 equals minus 2.5. And alternative hypothesis is beta 2 larger than this value. So this is a one-tail test. It's different from what we have seen in the previous page with two-tail test. So this is a one-tail test. So which means we only want to test here. So all the 0.05 alpha level stay here. So say if we get the t statistical value in this area or get the p-value less than 0.05, then we will say reject the null hypothesis, right? So we do not need to take care of this side, only this side. So we just fill in all values from the estimation. So this is the point estimate for the beta 2, and we minus this value, actually is plus 2.5, then divided by s. S is the sum of square of error, then divided by n minus k minus 1, then take a square root. And this is the C22 from the independent variables matrix, the multiplication for the transpose and inverse matrix. This value from this matrix, so we get 2.39. And we calculate probability of this statistic t distribution larger than 2.39 is 0.04. So this is the p-value from the data. So if we can see the p-value is less than 0.05, so which means this t statistic is located in the shaded area in the t critical value on the right side, right? So we conclude that we will reject H0 and in favor of H1. So say we conclude that beta 2 is larger than minus 2.5. Hello, welcome to our channel for probability and statistics. In this video, we will talk about confidence interval for the mean response in multiple linear regression. So if we have estimated a multiple linear regression model, so one of the purpose of using this model is to predict the mean response value from given independent variables value. Let's say this is the multiple linear regression model written in matrix form, because here X, so here Y is n times 1 column matrix, same for this error term, and X is the matrix for n observations and k independent variables plus a constant value, a scalar column, and a beta is a vector for the parameter. So the result is n response Y. So say if we want to estimate the mean response of Y, we call Y0 from the given variable of x1, x2, 0, xk0. So we can return mu Y given x10, x20 until xk0. So what does this mean for the mean variable response? So because we have estimated the confidence coefficient value, then we can just put in x variable. Here we can get a point estimate for the y. And we can omit this because this is the random term, or epsilon means value is 0. So the mean value of y, point mean value of y, is just calculate with this term, fill in x variable and times the coefficient estimated. But for the linear regression, this is a random variable. So if we say test 100 different mean variable, it should be different because this term, right? So this mean value of y is a random variable. So random variable, which means it has a confidence interval. And some mathematical results of this topic is for the mean variable y, so we call the y hat, there is a variance. So this variance equals epsilon's variance, the random term's variance, or sigma square times this term. This term comes from independent variables information. So x0 quote is this row matrix, and x0 is a column vector, and this term is the multiplication of a row and column matrix of x. So this is constant. So all information from this term come from independent variable. So if we know this term, then we can know the variance of y hat. So we can configure a confidence interval. But the difficulty is when we never know this one, because this is the theoretical epsilon. We never know this. So that's why we have to use the s square. S is the square root of s square, which is the estimation of sigma square. So if we use s here, we can get a confidence interval for the mean response of y given x variable. So this is the y hat 0. This just fill in, get a point estimate from the equation minus this term, and this is the y hat plus this term. This is the lower bound and this is the upper bound. And if we look at this term, t half alpha is the critical value of the t distribution with n minus k minus 1 degrees of freedom. K is the parameter number, how many parameters, how many independent variables in the module. And how to calculate S? if we look at this ANOVA table in multiple linear regression, we look at SSE, which is the sum of square error term. So E, error, is the difference between observed y value and estimated y value for individual x variable, right? So this is from the observation. So in all the observation, we can get error between the y observations and the fixed value of this observation. So they are not the same and get an error term. Then we take square of each error term and put it together. So this is called SSE. And SSE divided by n minus k minus 1 called mean SE. This is S square. This is S square. Then we take a square root, can get this S. So everything is ready, and we can calculate the confidence interval for the mean value of y given x value. So next we look at an example. So this example is for the percent survival rate of sperm in a certain type of animal, and after storage was measured at combinations of concentration of 3 variables. So this table listed the y value and x1, x2, and x3. And the question is, construct a 95 confidence interval for the mean response when we know these 3 independent variables. So it is quite clear. We just calculate this y hat point value by filling each term in linear regression equation. So we can get about 24.2. So next we can calculate this term, x vector and its transpose, and this matrix take inverse. So we can get this value is about 0.12. Then we used all the information, can also calculate the S square and S value. And from the t distribution table, we can find the t critical value for the 0.025 is about 2.2 for the 9 degrees of freedom. So because we want to calculate the 95% confidence interval, so which means alpha is 0.05 equals 1 minus 95%, right? So half alpha is 0.025. So that's why we calculate critical value here. So we fill everything in the confidence interval, can get about 25.89 for the confidence interval of the mean response value at these 3 independent variables. Hello, welcome to our channel for probability and statistics. In this video, we will talk about confidence interval for a single response in multiple linear regression. So we know if we have established a multiple linear regression model, one of the purpose is to estimate or predict the value of y or response given the values of independent variable x. So here we write a matrix form because there are more than 2 independent variables in x. So y equals x beta plus epsilon. So this equation says for the given values of x or independent variables, the mean value of response is y. So after we have estimated the coefficients of beta, so we can estimate the mean value of y and the confidence interval of mean value of y. But how can we estimate a single response and its confidence interval of y, not the mean value? So first we have to know some notations. So X is a matrix or the vector 1, then the value of X for 1 independent variables, and X quotes X, then inverse means inverse matrix, and this is the matrix multiplication. So there is the result is like this. This is all the known values from X. And this is ANOVA table. We have to know SSE. SSE is the sum of squared error. So what is error? Error is the difference between the estimated Y value in module and the real value or observations. So we just times X and beta, we will get the Y hat, Y estimated value. And the observation is Y. So their difference is error. So we take all the error square and sum together. This is SSE. Then SSE divided by its degrees of freedom, n minus k minus 1. So this item called S square. So S square is SSE divided by n minus k minus 1. So this S square is also called mean, MSE. So after we have know these notations, so the point estimate for a single response of Y actually is the same as we just fill in the coefficients and X matrix and time together. So we can get Y hat or Y0 hat. This is the point estimate for a single response. Actually is the point estimate for a mean response in multiple linear regression. This is the same. But the difference is for the confidence interval, this single point estimate will minus a term, also plus a term. This is lower bound and this is upper bound. So this is confidence interval. And this term is the multiplication of 3 items. The first item is T half alpha. So this is the critical value of the T distribution with n minus k minus 1. So for example, alpha is 0.05. So we can say we get confidence interval 95% of prediction interval for the single response. So 95% confidence interval, then T half alpha is critical value of T 0.025. Because alpha is 0.05, so divided by 2 is 0.025. T half alpha critical value with this degrees of freedom. We will check the table and get the value of this critical value. The S is the square root of S square, which we have seen in the previous page, MSE. Actually is the SSE divided by n minus k minus 1. Then take square root. This is S. Then is a term with the square root. So inside the square root is 1 plus X is a vector, X is a vector. Then this is inverse of multiplication of X matrix. Then plus 1. Plus 1 here because for single response, it is more random. So the confidence interval is wider than the mean value confidence interval. So that's why we add 1 here. Add 1 here inside square root. So if there is no 1 here, then this is the same as the confidence interval for the mean response in multiple linear regression. So everything is clear. Next, we take a look at an example. Example is a table with Y variable x1, x2, and x3. And the question is construct a 95% prediction interval for an individual percent survival response when these 3 X variables are known. So it's quite easy. We just fill in first solution for the Y variable. Then we can get X projection matrix and vector get this value, and this is a y single value, single estimate for the response. Then we can fill in odd matrix notation. We'll get S square and S and T critical value. Then fill in this confidence interval for a single response, and the result is about 90 to 29 for the single response confidence interval. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about choice of multiple regression model with coefficient of determination. So we know when we have a multiple linear regression model, for example, y equals x times beta plus epsilon. So where x is a matrix and beta is a column matrix, epsilon is a random term with the mean 0 and standard deviation sigma. So sometimes we only want to know what's the best model involving a couple of independent variables to estimate the response. So in this case, the criteria for saying which model is the best is to using the R square. This is the coefficient of determination. And R square is SSR divided by SST. SSR is the fitted value minus the Y mean value. So all the fitted value minus the mean value, then take a square, then take sigma for all the observations. And SST is all the observations Y variable minus mean value of Y. Then take a square, then sum together. So the result actually is 1 minus SSE divided by SST. SSE is the sum of squared error. Here error is the estimation of the epsilon. So SSE is the sum of the squared error, which is the difference between observed and fitted value. So here is a fitted value. So this is R square. So for example, we estimate the model and get SSR divided by SST equals 0.9117. So which means about 91% of the variation of the response variable can be estimated by the model. So this is a quite good number because about over 90% of the variation is estimated by the fitted model. And regression, sum of squares can also be used to give some indication concerning whether the model is adequate, because we only know the 91%, but we do not know it's enough to say this model is significant. So in this case, we have to use ANOVA, and this is F-test. F-test is two parts. The numerator is the SSR divided by its degrees of freedom, K variable, and denominator is SSE divided by its corresponding degrees of freedom. So if this numerator part is very big compared to the denominator part, so F will be very big and it will be significant. So the model is quite good. So for example, we get F equals 30.98, and we check the F critical value. For this value, the p-value is very, very small, so the model is quite significant. And we will reject H0 H0 is the model is not significant, and we will reject H0 at alpha level of significance, and we say the model is significant, and the combination of those independent variables will have explaining power to estimate the response variable. But we have to note some important things about coefficient of determination. So first, the linear regression model for X is not the only model. So we never know the real model. What we can do is only based on the theory and the availability of the data, which are our best to establish a model. So this is not only models that can be used to explain the data. And second, the model might have been more effective with the inclusion of other variables, or maybe the deletion of one or more variables in the model. So, and one thing about R-square is R-square will never decrease if we add more variables in the model. So that's why the R-square is quite limited, because it is sacrifice of the degrees of freedom. And it will, if you add more variables, the model will be overfitting, and even R-square will be close to 1. So in this case, the model is meaningless because we add many irrelevant variables in the model, but the R-square will increase anyway. So that's why we will find an called adjusted R-square. So this is 1 minus SSE with its degree of freedom and divided by SST with its degrees of freedom. So this value will not necessarily increase with the inclusion of more variables in the model. So for example, if the full model with 3 independent variables, so we get R adjusted square is 0.8823. But if we remove one variable from the model, so here deletion of x3, then we get the reduced model's adjusted R-square is 0.8904. So here you can see less variables in the model will get higher adjusted R-square. So R-square adjusted value will indeed favor the reduced model, and suggesting that the reduced model is preferable to the model containing all 3 regressions. So say if we want to compare the models using R-square, it's a better way to use adjusted R-square. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about tests on an individual coefficient in multiple linear regression model. So if we have a multiple linear regression model, y equals x beta plus epsilon. So epsilon is a random term with mean 0 and standard deviation sigma. And x is the matrix of independent variables. And beta is a column vector for the coefficient. So if we have estimated this model, get the coefficient beta. So next step, we most probably will want to test if each of the individual coefficients is significant, because the addition of any single variable or single coefficient to a regression system will increase the regression sum of squares and thus reduce the error sum of squares. And this addition may not be necessary, because if the addition of the variance estimated by the model from the single coefficient and from the single variable will be very little compared total variance of error term. So maybe this coefficient or this variable cannot be added into the model because this is the overfit of the model. So we have to test the significance or the effectiveness of the inclusion of single variable. So first we show some mathematical notation. So this is independent variable plus a scalar vector. And this is x transpose times x and takes inverse. Then we'll get a scalar matrix C00 to C22. And for the ANOVA table, for linear regression or multiple regression model, this is the SSR, which is the variance as explained by the module. And this is SST for the total variance of the response variable. And the difference of these two called SSE, which is error terms sum square. So error term take square and take sum, then divided by its degrees of freedom called MSE. We will also call this term as S square. So S square is estimation of the variance of epsilon. So we have this mathematical notation. So next we will test, say, single coefficient if it is significant. So from the examples we have shown in many of the videos in this channel, so we get, for example, a linear regression model with 3 independent variables. And now we will test if the third variable, beta 3, is significant or not. So the null hypothesis is beta 3 is 0. And alternative hypothesis is beta 3 not equals to 0. So we can use the t-distribution or t-test for this beta. So this B3 is the estimation of the coefficient from the module. Then we minus 0, then divided by a term. This term is the product of S. S is the square root of S square. And take a square root of C33 in the previous matrix. So this term, projection, actually is the standard error of B3. So the division of these two parts will be minus 0.556. And this follows a t-distribution with 9 degrees of freedom. So you can see this term is not in the critical region, because the critical region is about minus 2, less than minus 2, or larger than 2. But this value is between these two critical values, so it's quite not significant. And this indicates beta 3 does not differ significantly from 0. We will hold this null hypothesis, and we can say we have to remove x3 from the module. So this is the t-test to test the significance of one individual variable should be included or not included in the model. And if we use another alternative called f-test, an f-test actually is an ANOVA type test. So if we calculate amount of variation in the response that is attributed to x3 in the presence of the variable x1 and x2, so we have to calculate this term called R beta 3 given beta 1, beta 2. And this term is the total SSR. SSR, if we look at the table, so this is the SSR. We include 3 variables in the module, and this module can explain how much percent of the variation of the total SST of the response variation. So this is SSR. And this SSR minus another SSR we called R beta 1, beta 2. So R beta 1, beta 2 is a module which having not variable 3 in this model, only variable 1 and variable 2. So the difference of these two variation explanation by these two models is the contribution of variation explained by only variable 3. So this term about 1.33. So this actually is a very small proportion of the entire regression variation explained by this variable inclusion. So we have to test using ANOVA. So ANOVA is the F-test, which is two parts of variation division. So first is the variation by variable 3, because it has only 1 degree of freedom. So we can omit division by 1. And S square is the total error sum square, which is the SSE divided by its degrees of freedom. So the division is an F value, is a value followed with 1 and 9 degrees of freedom of a F distribution. So you can see this is not significant in the F-test also. So we'll get the same result as we use the T-test for the significance of these coefficients. And if we record that the F-test actually is, if F-test with 1 and V degrees of freedom, actually same as a T-test with V degrees of freedom. So the T-test statistic take square actually equals F statistics in the model. So if we look at F value here, 0.309, actually it is the square of the T value of minus 0.56. So these two kinds of tests will get the same result. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about tests on significance of a subset of variables in multiple linear regression. So when we have estimated a multiple linear regression models, we are very interested in the coefficient significance. And similar as testing for single variable parameters or coefficients significance, we can test for the significance of a subset of the variables simultaneously. So for example, if you want to know if the importance of including both variable x1 and x2 in the model significant, then we can test the hypothesis H0 and null hypothesis, both beta 1 and beta 2 equal to 0 simultaneously. And the alternative hypothesis is beta 1 and beta 2 are not both 0, which means at least or both of them are not equal to 0. So if you want to test like this is the ANOVA test, and we have to use the F-test. So here F-test statistic is calculated as the division of two parts. In the numerator is the RSS of both beta 1 and beta 2 and divided by the 2. Here is the degrees of freedom. And the denominator is S square. So what is R beta 1, beta 2 given beta 3, beta 4, beta k? So this is the difference between the whole model's SSR, sum of R square, sum of regression model, then minus the sum SSR of without beta 1 and beta 2. So we have to estimate two models. The first is the original whole model, including beta 1 and beta 2. They will calculate SSR. And the second model is without beta 1 and beta 2, we calculate SSR. Then division of these two and divided by 2, because we have two parameters to test here. Then S squared, we look at this ANOVA table. So SSR is the sum of regression, which is the variation of the observations Y given by the model. And S squared is the mean SE. Here is S squared, which is SSE divided by n minus k minus 1. So SSE is sum of error squares, which is the error term sum for all the observations. An error term is the difference between opposite value and the value on the regression line. So SSE is the difference between SST and SSR. So SST is the whole sum of variation of the observations against its mean. So in our example, we'll test. Sorry, here is both ways. Here beta 1 and beta 2. Oh, sorry, here beta 2 and beta 3. If we want to test these two, then we will calculate only the model with one variable, SSR. So we calculate the SSR for the model with only one variable, beta 1. Then this is SSR calculated, and S squared for the full model. And we also calculate the SSR for the whole model. So the F-test statistic is R's beta 1, beta 2 only. Then we calculate the RSS for the whole model minus RSS for only one variable, beta 1. Then divided by 2 in the numerator. Then the denominator is S squared. So we have all these values filled in, then we get F-test statistic is 24.68278. So this F-test is not significant. So this test is significant. So which means we will reject the null hypothesis and we will say both beta 1 and beta 2 are not simultaneously 0. So we hold H1 and reject H0. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about regression with categorical explanatory variables. So when we have applications with multiple linear regression, sometimes the variables are not all continuous. So say, in this example, x1, x2 are continuous random variable, and say is not continuous. They are categorical variables, or say dummy variables. So for example, if we say has 3 categories here, so we have to include 2 dummy variables. So for one dummy variable, say 1i, say 1 here, we will put 1 if the categorical, for example, is 1. So we decide the first category for this dummy variable is using say 1. So we just put 1 for variable's value in observation. And for the second category, we will put say 2 with 1. So one category only appears in one dummy variable. The second variable will be 0. And the third category will have 0 for both variables. So we look at an example. So say this example for the y is amount of suspended salts, and the variables xi is a pH, and the polymer is another variable, which is a categorical variable with 3 categories. So in the regression model, we just put beta 0 plus beta 1 xi. I is for the observations. There are total 18 observations. this table, there are total 18 observations, but for the polymer, this is categorical variables, their category. First 6 has category 1, and second part 6 with category 2, and the last part for the category 3. And this is continuous variable for the x. So the model established is x is beta 1, and for the beta 2 and the beta 3 is for the dummy variables with first and second category. So for the category 1, for this polymer dummy variable, we just put 1 for this value. And for the second category, we just put 1 for this variable. And for the other is 0. And for the third category, for both are 0. Right? So if we look at the previous page, so it's quite clear. For the category 1, actually, the model is expectation of y is beta 0 plus beta 2 plus beta 1x. And for the second category, the model will become expectation of y equals beta 0 plus beta 3 plus beta 1x. And for third category, the model will become with beta 0 plus beta 1x. So you can see for the dummy variable, it comes with the change in the intercept of the model. So the slope is the same. Slope are the same. And intercept is different. For the change comes from the parameter for 2 dummy variables in a 3 category of 1 variable, right? So the estimation is the same as we have old continuous variables, because we just fill in the 1 for this dummy variable, and with the parameter actually is the parameter change for the intercept. So after estimation, same as with a regression model for all continuous variable, we get this parameter estimation. So the parameter estimation, we check in this example all significant. So Z1's parameter is beta 2 and Z2 is beta 3, right? So this is beta 1, beta 2 and beta 3. All significant. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about varying slope in regression with a categorical interaction. So we know if in a regression model there are categorical variables, or say they are dummy variables, so usually the dummy variables value 1 and 0 or 2 with multiple categories will have effect on the intercept of the model. But sometimes we will also test if dummy variables value will have effect on the slope. So which means if the dummy variables have interaction term with the continuous variable. So say in this example, there are 1 continuous variable and 1 dummy variable. So x is continuous variable and z is dummy variable. So we can test with such a model, beta 1x plus beta 0 plus beta 2 times z, because z here we assume are 2 levels, so only 1 dummy variable beta 2 is needed. And we add another term, beta 3 times xz. So this is the interaction term. So after the estimation of the model using the data, say we can see here x, z1, z2. So here z2 means the interaction term. So both x, z1 and z2 parameters are significant. So all these 3 items will be included in the model. So if we look back again, for categorical c equals 1, the module becomes in this expression. And for the c equals 0 will be the simple expression. So which means we have both odd parameters are significant, though these two modules will have different intercepts and slope. So they are both varying intercepts and slopes for the two categories in the module. So if we look at this figure, you can see this is the module in which the categorical variable is 0, and this is the module for categorical variables equals 1. So these two modules are non-parallel and have different intercepts. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will explain stepwise regression. So we know in regression analysis, we build a model and want to include which variable will be present in the model. And sometimes there are concrete reasons to include several important variables in the model based on previous research questions, the results. And in other cases, we will include the several primary variables based on the sample data. So in such a situation, one kind of approach called stepwise regression can be used. And for talking about the stepwise regression, we have to first understand the forward selection and backward selection, or backward elimination. So these two opposite process. So the forward selection is start with only one variable, or start with a simple linear regression. So we will find the largest regression sum of squares for this variable if we include one of these variables in the module. So say if x1 gives the largest value of r square. R square is the coefficient of determination. So this is the variation of the model to explain the variation of the observations of the y variable. So in this case, we will start with x1. And next we will test if x1 is significant, the coefficient is significant or not. So if x1's coefficient is not significant, so the process will be terminated. So there is no possible module. So if x1, which gives the largest value of r square and it is significant, then we will continue in step 2. So step 2 will choose one of the rest of the variables given x1 is in the model. So this will based on, we will calculate several models which include xj. So xj is the rest of the variables except x1. So say if we get how to calculate the r square. So r square xj given x1. So x1 is the coefficient is beta 1, right? So we will calculate both x1 and xj in the module, then minus r square of the module only x1. So this is the r square increment. So the variation explained by the model, but this is the marginal increment coming from the variable j, right? So we do this process for all the other variables. Then we will get r square, which is the best one, the largest one. Then we will include this variable in the module in addition to x1. So for example, x2 has the largest r square. Then we include x2 in the model. Then next we will test if x2 is significant or not. So if x2 is insignificant, so the process is terminated. The model has only one variable. one independent variable x1. So if not, which means x2 is also significant, then we go to step 3. So we process this step and so on until there is no more variables will be added into the model, then the process is terminated. So this is forward selection. And this model is continued until the most recent variable insert fails to induce significant increase in regression, right? And such of the test, significant or not, is based on the f-test. So f-test, for example, we have one variable beta1, then we add beta2 or add x2. Then this test, f-test, can be done with r square increment from x2 divided by s square. So s square is the mean squared error for the model, including x1 and x2. And for the third step, similarly, r square increment from beta 3 from x3 divided by s square. Here s square is the 3 variables included in the model. So all these f-tests will determine if this variable is significant or not, right? So there are degrees of freedom in each step of the f-test. Here n is the number of observations, and 3 is 3 parameters. So this is a forward selection. And what is the backward elimination? This is the opposite of the forward. So backward, we select all 5 variables, for example, in the model first. Then we will calculate if we remove beta 2, for example, then we will get f-test if it is significant or not. If we can remove this, then we'll get the decrement of beta 2, right? So if the test is insignificant, so which means we remove this one, and the model will not be worse, right? So we just can remove this variable. So, and so on. This process and so on until there is no more variables can be removed. So if we remove this variable and the decrease of the r square, margin r square, is significant compared with the s square f-test, then we cannot remove this one. So if only insignificant for f-test from removing one of the variables, then we can remove this. But we will find the biggest one, r square removed. So this step is backward step. So stepwise regression is combined with is a forward type. But in each step, in addition to add one variable into the model, we will test all the variables again. Because, for example, if we add one variable beta x2 in the model and with the current variable x1, so also in the previous step we have tested x1 is significant, but because we add x2 in the model, we have to test x1 again. So this is the stepwise. So each step, some of the variables can be removed with the addition of another variable. Then again, in the next step, we will also choose this removed variable again to the model. So it's quite complicated, and stepwise regression can have multiple times of addition and removing of one single variable into the model in different steps. So we will show an example which estimates the length of inference based on the weights and several variables of the inference at the birth state. So we do not show the table, but we will show the calculation. So considering each variable separately for individual simple linear regression equations are fitted. Because in the first step, we will have 4 independent variables to select. So we have to estimate 4 simple linear regression with only 1 variables. And the following is the regression sum of squares. So R square for each variable. So variable x1 clearly gives the largest regression sum of squares. This is the largest. So this is the candidate for inclusion in the first step of the model. And the mean square error for the equation is S1 is this number. So we will test if it is significant to include this variable in the model. And we get F value and for 1, F test for the 1 and 7 degrees of freedom because we have all 8 observations. So here is 7. And this number is significant. So X1 is included in the model for first step. And step 2, there are only 3 variables left to evaluate. So we again will test R square for 3 model. Each model has 2 variables, x1 and one of the other of 3 model variables, right? So 3 equation gets R square. So x3 here has the largest increment of coefficient of determination. So this is the candidate variable to include in the model in the second step. Then again, we test with the F statistic if we include x3 in the model and with x1. So this is the number, and now the degrees of freedom is 1 and 6 for the F test. Again, this is also significant that we include in the model. Now, we have to subject x1 in the presence of x3 to a significance test. Why? Because this is not a simple forward, because we use stepwise. So, because we have added x3 in the model, we have to test x1 again here. So test x1 is using this form, and this is the test for F. So x1 is also significant with the addition of x3 in the model. So step 2 is completed, and both variables x1 and x3 are significant and have to be included in the model, right? So in the step 3, because x1 and x3 already in the model, we now require 2 equations for the linear regression to estimate if we can add x2 or add x4 in the next step. And we calculate R square for these 2 variables. If we add this in the model, I can see R square for beta 2 for the x2 quite small, and for the x4 is also quite small. And S square for these 2, neither is significant at alpha is 0.05 level. So we will stop at this step, and the final regression model will be having 2 independent variables, x1 and x3. Then we can estimate with the coefficient, and the final R square for determination is about 0.9882. Just one comment of this process. So because the stepwise regression is graded, right? Because in the first step we find x1, and x1 then we add x3, right? And we will not consider other case. For example, if we add x2 first, or we add x4 first, or add x3 first. In many kinds of combinations of the model, we just start with the x1 first. So it is not necessary that this result will be the optimal case of all possible models, because all the possible of the model is about 4 times 3 times 2. There are about 24 different models. But we only consider starting from x1. So this is a graded process, and not necessarily the complete optimal result will be found. So we just note, but it of course will be very, very close to the optimal, or maybe the best one. So we have to note this, because of course this is also from the sample data. We only from the sample data, this is random. If we get different samples, we'll get different results. So this is maybe the best case, optimal case, what we can do compared with the time cost and the precision, what we can get, right? So this is the stepwise regression. Thanks for watching.
Hello, welcome to our channel for probability and statistics. In this video, we will show theoretically how to detect outliers in regression using studentized residues. So we know in a linear regression model, for example, there are 2 independent variables, x1 and x2, and y is the dependent variable, or the observations. So, and if we want to check which is the outliers, observations by observations, so we can write a row vector for this observation, xi, and xi is a vector with these rows independent variables. So 1 to k means there are k variables, k explanatory variables in the model. So this is a row vector particular for these observations, x variable. Then we will show there is a scalar value called hii, which is xi's row vector times this capitalized X is the matrix for all observations, explanatory variable part. So this transpose and times this matrix, then inverse. So this part right multiplied with this row vector, then times this column vector. So the result will be a scalar value, right? So this value will be used further by calculate this EI is the difference between the observed Y and observed and regression value, hat value of this Y. So this is the EI, the residue of this observation. So this residue we divided by the variance, a square of the variance of this residue. So this is so this part is a standardized residue, right? So here is the modulus sum of squared errors divided by n minus k minus 2. K is the number of parameters. Then take a square root. So this is S. Then here we fill in HII, then 1 minus HII, then take a square root. So this part is called studentized residue. So if this value is T-like statistic. So if this value is significant, it will be skeptical that these observations is outlier. And we can also go further to use another S. So this S is estimate of the error standard deviation, which is calculated with this observation deleted. So we write S minus I. Here HI and EI is same as before. EI is the residue and HI comes from this formula. So this item also follows t-distribution, and this is called R student value. So if this value is significant, then it will also skeptical that this observations is outlier. So next we will show example. So here is the data for the y and x1 and x2. Then after calculation, we can get a table. For Ri, this is student-sized residue, and Ti, this is student t-value. So you can see the false observation for these two values very large. So if it is not outlier, it will be around 0. Okay, all other values around 0, very close to 0. But these two values larger than 3. And for this t-value, particularly very large, almost 10. So in this sample, we have to check in particular this observation as outlier. Thanks for watching. Hello, welcome to our channel for probability and statistics. In this video, we will talk about how to select a best regression model using plus residues. So we know in model selection among alternative regression models, usually we will think about which model will best predict or estimate the mean response of the model, of the data. And experiment should take into account the relative size of the S-squared values for the candidate models and confidence interval of the mean response. At the same time, we will also consider how well the model will predict response values that were not used in building the candidate models. So this means the model is used to predict the unused data, right? You got estimation from the current data, but the purpose of building the model is to predict the unseen data. So this idea is same as the cross-validation in machine learning. So in regression model statistical data analysis, we can use one kind of called plus residues associated with cross-validation errors. So plus here means prediction sum of squares. If we look at this expression, delta I equals yi minus y hat I, then minus I. So here I is 1 to n for n observations. So here y hat I and comma minus I means in estimation the model, we do not use these i's of data. We use these i's of data only in the model prediction. So, for example, we have 100 data observations, then we take one of them out, and we use the rest 99 observations in estimating the model. Then, we use the coefficients with the model estimated to predict these i's data. Then we get this residue. So this residue called plus residue. And we can use absolute value of the plus residue for each i's observation. Then take a sigma, or we can use the square, then take a sigma. So these are criteria for choosing the model based on plus residues. And in addition, we can use the R squared, but here R squared is called prediction R squares. So coefficient of determination, but we used delta I here. So here is a plus residue square here, sum of square, instead of SSE in the usual case. So this value is also between 0 and 1. So we take an example. So this data, 13 observations. This one is y value and this 5 for the x value. And we want to choose among best model, including some of the variables or all of the variables of these 5 variables. Then, with the plus residues estimation from software, so we can get all these values is square, then plus absolute value of plus residue, and the sum of squares of plus residue, then R square. So from this criteria, we can choose this the best one, because this has the highest R square and the lowest of plus residues. So which means the final model will be only 2 variables, x2 and x5 in regression. Thanks for watching.
Hello, welcome to our channel for probability and statistics. In this video, we will introduce the basic ideas of linear regression model. So linear regression or regression is used to find some inherent linear relationship among the variables. So here you can see y equals beta 0 plus beta 1 multiplied with x. And this equation y equals beta 0 plus beta 1 x1 plus beta 2 times x2. So this one is only 1x and this one has 2x. So here this is a simple linear regression and this is a multiple linear regression. In all these two equations, y is the response or dependent variable, like house price and child weight, and x here are regressor or say independent variables, just like size of the house and age of child. And if we look at this figure in simple linear regression, we can see a straight line because this is linear equation. Why we call linear? Because beta 1, beta 0 are only a scalar. But x here can be x or x squared, no problem. So linear means the parameter is linear type. If x divided by beta 1, it's not linear for beta 1, right? So x times or x multiplied with beta 1, this is linear for the parameter. So for simple linear regression, we can show dependent variable and independent variable in a straight line in this figure. And beta 0 is the intercept, and beta 1 determines the line's position or the angle of this line. It's a coefficient. So we can see it's a deterministic relationship between two scientific variables. But why in real world, if the same child with same age, but they have different weight, and the same age or same size of the house have different price? So, which means in the relationship between x and y, there are plus some not deterministic factors, right? So, this is the concept of linear regression analysis, and we will use a statistical model to model this relationship. So, the actual y is the opposite of the value equals beta 0 plus beta 1 times x, also plus a random term. So here, this random term epsilon is a random variable that is assumed to be distributed with mean 0 and variance sigma square. And variance sigma square is the same for odd value of x. So this is very important. We will show later in the figure. And this is called homogeneous variance assumption for linear regression model. Say single linear regression SLR model. If we look at this figure, based on previous beta 0 plus beta 1x, this is straight line, we also plot the real opposite of the value. Because this is straight line, you will never know. You will never know. Nobody will tell you this is straight line. What's the beta 0 and beta 1. What we know is the opposite of the value for this point. This point can be stay here, can be stay here. For this x value, the point can be stay here, also can be stay here. But if we have many x value for the same x value, odd random term epsilon will follow some distribution which has the same variance, no matter which x value here is, right? So this is called a homogeneous random variable. So this is a very important assumption. If we look at this figure, x1 to x6, and this figure shows like a 3D figure in the two-dimensional space. So this is x and this is y. This is the deterministic relationship between x and mu y given x. So this line can be seen as the average value of a given x for the dependent variable, right? And this shape model the random term, the distribution of the random term epsilon. So that's why you can see your opposite value maybe here or maybe here, different value. But for the different x, their distribution of this random variable are the same. So the epsilon has the same distribution for different x value. So in a regression model, x or the independent variable, this is deterministic. This is not a random variable. Just like a house age and child age. This is deterministic, not a random variable. And what we observed, the value, like a house price, the weight of a child, this is random because this opposite value has included a random term upon this deterministic relationship. And why we want to do analysis with the with the regression model? Because we want to know the parameter. And why we want to know the parameter? Because usually an analyst based on previous research results or from literature review, anyway from some no information and no theory, then build such a model, but never know the real beta 0 and beta 1. So we have to estimate these two parameters, but we never know. See, only what we know is the opposite of the value for the y and the deterministic value of x, right? So from this value, we can estimate this regression line. We can estimate and using beta 0 for the estimation of B1 as estimation of the beta 0 and B0 estimation of for the beta 0 and B1 estimation of the beta 1, right? And this equation can be written as the y hat equals beta B0 plus B1 times x. So y hat is the predicted or fit the value from the estimated parameter. So beta 0 and beta 1 is estimated parameter. This is real value, right? And we show in this figure, one is one is the theoretical value, but we never know this value for beta 0 and beta 1. And the other line, very close but not exactly the same. This line is y hat equals b0 plus b1x. So this is estimated or say fitted line from the given observation of these scatter plots. And we look at these two equations. So yi is the opposite of the value. For the fitted line, b0 plus b1 xi, we have to add ei. So this is the regression fitted line's error term. And for the theoretical regression line, yi equals beta 0 plus beta 1 times xi plus epsilon I. So epsilon I is the difference between the opposite of the value and the deterministic relationship theoretically, right? But we never know these two parameters. So in this figure, you can see epsilon is opposite of the value minus mu yx equals beta 0 plus beta 1 times x. And error term ei is the difference between opposite of the value and the fitted value from estimation, right? So beta 0, b1, b0 and b1 here are the parameter estimated. So we can talk about the method of estimation. And the method of estimation widely used in regression model is the least square. So we should find b0 and b1, which are estimates of the beta 0 and beta 1, so that the sum of the squares of the residue is a minimum. So the estimation process is optimization problem. So we have to make a minimum of this error term in between the fitted line and the opposite of the value. And the residual sum of the squares is often called the sum of squares of the errors about the regression line and is denoted by SSE. We look at this figure again. This error term, EI, take sum, then put together this summation of these error terms square called SSE. So if we make this sum of the squares minimum, then we can say this line will be best fit with the theoretical line. So mathematically, if we want to get the SSE, we can just write this form. The difference between y is opposite of the value and the fitted value. Then take a square, then sigma for all observations. Then SSE make differentiation of SSE with respect to B0 and B1. Because we want to estimate these two parameters. So we make differentiation. Then this is the result of the differentiation. And then we set these two partial derivatives equal to 0 and make some manipulation. Then we can get sigma yi equals this 4 and sigma xi yi equals this 4. Then from these two, we can get the parameter B1 and B0. Actually, B1 is a division between the cross products between x and y and divided by the second moments of x with the mean of x. And beta 0 is a very simple form. So next we show an example using linear regression module. So this is a table of some data. The y value here and x value here. So y is the oxygen demand reduction and x is the solids reduction. So we estimate the regression line for pollution data in this table. So the solution is quite easy. We just fill all data and get several results for xi sigma, yi sigma, and xi yi and xi square. I will take sigma. Then we just fill this number in B1 and B0's formula. So we can get these two parameters. So which means y hat or the fitted line, this is the results for the fitted line. I'll say y hat equals beta B0 plus B1x here. And from this fitted line, we can also get 1 point estimation or prediction. Say, for example, 31% reduction level, we can get 31 reduction in the chemical oxygen. This is y hat when the x, or say the reduction in the solid is 30%. So next videos we will go into more details and assumptions and more advanced topics around linear regression module. Thanks for watching. So, welcome to our channel for probability and statistics. In this video, we will talk about the mean and variance of the estimators in linear regression. So we know linear regression is just a linear model used to find some inherent linear relationship among variables. So this is a simple linear regression model because there's only one x. Here x is the regressor or independent variable. And this is multiple linear regression because there are two independent variables, x1 and x2 here. So for the simple linear regression, we can use a straight line in the two-dimensional space to depict the relationship between x and y. So this is the beta 0 parameter for the intercept, and beta 1 is the slope of this line. And the estimation of the linear regression model is based on the idea that we will minimize the sum of the squares of this E1, which is the error between the observations x, I, y, I, and this fitted line. So y hat is the beta is B0 plus B1x. So B0 is just the estimation of the beta 0. Because beta 0 plus beta 1x is the real line. But we never know this parameter. We only can estimate using B0 and B1 here. So this line is called fitted line or linear regression line. So the estimation of the linear regression is based on the least squares, which will minimize the sum of squares of this error. So the parameter or the point estimate of B0 and B1 is B0 is the y bar, the average of all y value minus average of x value times B1. And B1 is the sigma of the cross product of xi and yi with respect to their corresponding mean value, then divided by the sum of squares of the x or I with respect to the corresponding x bar's value. And we know it's very important that the values of B0 and B1 is random value, because this is just based on a given sample of n observations.